Okay, here we go. All right. Welcome, everybody. We're live. Sorry for a little delay, but it's just part of the fun of going live, I think. So welcome, everybody, to the live workshop. We're excited to share this with you. We know as we keep going, people will slowly be strolling in, and it'll be fun. So I guess to kick it off, we can just go at it. So I'm Isaac. I'm with Civil Engineering Academy. I've got Andy Richardson with me, and Andy helps to instruct our depth review courses. And we wanted to do a few of these live problem-solving workshops. We're excited to share them with you. So this first one that we're doing today is going to be more towards the water resources section. I think this is a section that's going to help everybody, whether you're studying for the FE, the PE, or your depth stuff. So a lot of these categories kind of mix into each of those exams, but we're excited to share this with you. Again, thanks for joining us. If you guys need a course and you're joining this live from anywhere, go check out civilengineeringacademy.com. Go check out the review courses, and you can go grab this particular depth course that Andy's teaching or anything else that we've got on there. So again, welcome. We're excited to share this with you. The exams are a big deal and a big milestone in your life, and we're just excited to help you out with that. So anyway, with that, I'm going to have Andy introduce himself, and then he can go to town.
All right. Thanks, Isaac, and thanks for putting us on this morning. So welcome, everybody. Andy Richardson. I'm an engineer and got about 22 years experience, so I got a couple years, and excited to be a part of this. Just a quick introduction of who I am to establish a little bit about a credibility aspect. Again, 22 years experience, do have a PE. I enjoyed the PE so much, I took it twice, but not that I failed. I actually took the PE civil, and then I took the structural 1 PE back when it was a thing. But I just enjoy and one thing about the exam, I always enjoyed studying, believe it or not. And so that was the reason that I've always just been a part of the PE community in terms of helping people pass. And so I did help teach with PPI for about 5 years, from 2012 to 2017, being PPI being the author of the Civil Engineering Reference Manual. Now it's under a slightly different name, but and then also wrote the course that we sell over at Civil Engineering Academy. So don't want to belabor that point too much, but wanted to give you a little bit about myself. You can go over to the Academy, find out more about Isaac and myself, who we are and why you should listen to us. But hopefully today will be a little bit more reason why. So I think we can go ahead and jump into some problems. Is that correct, Isaac?
Okay, let me add this. Yeah, let's do it. So I'll switch over to our problems, and you can go to town here.
All right, sounds good. And let me just make that hair bigger.
I do want to say, if you're active in the chat rooms, I'll be watching those. If you have questions about anything, don't hesitate to throw questions in there, and we'll get to them. So, I don't know if Andy's going to be watching the chat box very well, but I will be, and I'll raise a hand or whatnot and make sure we get some answers taken care of for you.
That sounds perfect. And do we have anybody yet in the comment section?
We don't have any comments yet, but we do have people joining us. We're up to about 20 people showing up, so that's kind of fun.
All right, awesome. Well, we'll go ahead and get started on these problems then. So today's focus, water resources, and I went through some of the products that we have on the course, and noticed that we did have water quality problems. Could use some more of those. So I went over to the NCWS specifications and looked up the specifications, and this is under water quality, under the water resources depth. So these are some of the topics we're going to be focusing on today in this. It's not a lesson per se, but it's practice problems, but these are the areas that we're going to focus on. So under water quality, it's worth about 3 points on the afternoon section of the water resources exam. And some of the questions include stream degradation, oxygen dynamics, TMDL, total maximum daily load, such as nutrient contamination, DO, and load allocation, and then also biological contaminants and chemical contaminants. So with that, we're going to go ahead and jump into our first problem. And the problem statement says, a wastewater treatment plant discharges into a nearby stream. The effluent is 8 million gallons per day with a DO concentration of 1.5 milligrams per liter. The flow rate of the stream is 150 cubic feet per second and has a DO concentration of 7 milligrams per liter. Assuming that the flow is immediately mixed, what is the DO of the mixed water downstream of the plant? Okay, so this is a basic mixing problem. And what we're going to use for that is this mixing equation. What I thought I had it written up there. I'll just rewrite it. We have a basic mixing equation, and it's another way to think about it is a weighted average. So the equation is going to be Cm, or C mixed, is going to be the concentration 1 times flow 1 plus concentration 2 times flow 2, and then divided by the sum of the two flow rates, Q1 and Q2. Okay, so we have some given information in the problem statement here that we can use. This is effectively Q1, we'll call it, the 8 million gallons per day. We'll need to convert that. And then this is going to be the C1, the concentration 1, which is the DO, the dissolved oxygen. And so what's happening in this problem is we have the wastewater treatment plant discharging water into the stream, and we have a final dissolved oxygen concentration that we need to determine. Okay, and this goes right into the water quality aspects that we're getting at. So this is a mostly related to the mixing equation, but it's a part of computing these type of problems. And so that's Q1 C1, and then we have Q2 C2. And so let's plug those in. Well, first of all, we need to go ahead and convert Q1 over to CFS so that they're matching units. So let's go ahead and do that. Q1 is going to be 8 million gallons per day. I'm going to say 8 times 10 to the 6 gallons per day. And then, of course, we know there's 86,400 seconds in a day. Some days seem longer than others, of course, but and then there's 7.48 gallons per foot cubed. And of course, the units there, 86,400, you can compute yourself really quickly. 24 hours, 60 minutes, 60 seconds, multiply them out. And then 7.48 gallons per cubic foot. And everybody's using different resources. A lot of you are probably using the Civil Engineering Reference Manual. And if you are using that one, they have conversions right there in the front of the book. So that's one good way to do it, or whatever units conversion index you have, that would be what you would refer to. So multiplying that out, we're going to get 12.4 cubic feet per second. And that's then next we just plug and chug. So C1 we said was 1.5, and we're going to keep our units, but I'm not going to write all the units out just for time's sake. 12.4 cubic foot per second. C2 is going to be 7 milligrams per liter, and Q2 was 150. And then adding the sum of those two, so 12.4 plus 150. Again, we have consistent units, CFS, at Q1, Q2 on the numerator, denominator, so that cancels out, and then we have the concentration remaining, which would be milligrams per liter. So doing the math, we end up with 6.58 is our quantity, and our units is milligrams per liter, which is going to be our concentration mixed, or our DO concentration, which is what the question asks for, of course. So that's what the concentration of oxygen is in this water body after the wastewater discharges it into the water body. That being said, So oxygen is obviously a big part of the water quality aspect. And so what we want to make sure of is that the water has sufficient oxygen to sustain fish life. And this would be right on the borderline. About 4 to 6 minimum would be what you would want. So we're right at that borderline, but milligrams per liter, that is where fish life and other aquatic life is needed to have adequate oxygen. Okay, so that's problem 1. Let's jump on to problem 2. And if we have questions, I'm sure, Isaac, you'll let me know. But
I will. Most questions right now are just related to people letting us know when they're taking exams, if there's going to be a replay of this. And I will say, if you do the replay of this, so we're going to keep it on our social channels for just a limited time, and then it will be taken down and moved over to our course. So if you do need a course, go check us out, civilengineeringacademy.com. You'll find it there. Another question came in from Danielle that said, for the non-computer-based test version, do they give you scrap paper for calcs, or is it similar to the CBT where it is like a whiteboard?
Mm-hmm.
So on the PE exam, you will have plenty of space to write out your problems in what they give you. So they give you your exam booklet, and they also give you your pencil, and you go to town with that. So there is no whiteboard. That might change. That will change when it goes computer-based in 2022 to be similar to the FE. But yeah, no other questions on the problem you just solved, though. So
okay, awesome. Well, I guess everybody's got that one covered then. And yeah, one suggestion too. I don't know if you have. I don't know, Isaac, if you have it on your website, but the NCSS sample exam is a really good way to get used to working in the workbook, because you're working off of their sheets of paper and you're kind of marking into a workbook. So it's a little different, and you also want to maybe practice using a Scantron as well. So not to mention the technical aspects and the type of problems that they have. It's a good idea to, and obviously you can assess yourself and make determination of how much you need to study. And but that's a good way to study is to actually do it in the workbook they provide.
I agree. Hey, and this next problem, you could actually ask our group and see who knows the answer to this one, I bet. So
okay, yeah, there you go. All right, so problem number 2, BOD. Which of the following does BOD stand for? Does it stand for A, biochemical oxygen demand, biological oxygen demand, biological odor disorder, so BO, or biochemical odor disposal? So which one do you guys think in the group there? And let's give you guys just a second or two to answer.
I guess while they're thinking of the answer, I'd like to just plug that theory on the PE exam is always a surprise for people with the amount of questions that they ask you. So be prepared for 10 to 15 questions that are theory, just straight up theory in the morning, and you'll get theory also in the afternoon. So don't be surprised by questions similar to this and others where you're going to have to dig up a definition or look in your book for something like this.
Yeah.
We're getting answers A.
All right, Danielle, good work. So it is A, biochemical oxygen demand. And you could have looked that up in your index pretty quickly, but yeah, that is the answer to that one. And let's do a little primer on what BOD is.
I like the odor disorder.
Well, we're in a live workshop. We're a little looser, a little fun, but we're still studying for the PE. It's just why not loosen up a little bit?
Nice.
So we got a primer on DO and BOD. So BOD, by the way, is the two go together. Okay, so BOD is biochemical oxygen demand, and what it is it's an indication of the waste that you have. So if you have a lot of waste, meaning wastewater waste, so organic is the the primary mode that we're talking about, organic waste. And it's an indication, it's the bugs or the microbes that are in, some people call it bugs because it's microbes. And so in the wastewater community, environmental community, they call it bugs, but it's actually the microbes. And so the more microbes you have more waste, right? And so the more microbes you also have more oxygen usage, right? And so they're needing, these bugs, these microbes feed on the waste and digest that, which is actually a really good thing because it makes it into an inert material. But it also is the digestion process. So that digestion process takes up a lot of oxygen. Okay, so if we can measure the oxygen levels of that water, then we know how much waste is probably in that water. Okay, so the BOD, biochemical oxygen demand, it's an indication of how much waste you have. Now there's what we call in order to determine what your BOD is, you do a 5-day test, which literally you just measure the dissolved oxygen in the water at day 0 and at day 5, and then, at day 5, and that tells you at 5 days what your demand is. Okay. Now that is an indication of what your BOD ultimate is, BODU, and so with that there's a correlation there. BOD 5 is correlated to BODU. So that's just a primer on BOD, and then this is a bit of a primer on dissolved oxygen. So with the BOD, the waste that goes into, like on the previous problem, we mixed in wastewater into a receiving stream, which is going to put a demand on the oxygen of that stream, right? Which is what we were determining what the DO is. So what happens on this slide, what we're seeing, this comes, if you are using the Civil Engineering Reference Manual, this is just a recap of figure 28.5. And what we have is the DO saturated at some level, right? Maybe it's 10 milligrams per liter, and it's the most oxygen that water can hold if it's perfectly aerated, et cetera, at that particular temperature. But as soon as whether we're disposing of wastewater or we're not really ever going to be at that perfect condition, right? Because we're not ever going to be perfectly aerated. So there's going to be a deficit. Unfortunately, the nomenclature here is D sub 0, and that's not the nomenclature I came up with, but that's your deficit D at time 0, right? So this is on the vertical axis, we have dissolved oxygen. On the horizontal, we have time. And so at some level, when we start out, we already have a deficit here, and then the dissolved oxygen goes down, and then it comes back up as the water has turbulence and such. Now this graph here is showing if you didn't have turbulence, if you didn't have oxygenation, then it would just go straight down. Okay, so this curve with the smiley face is really the dissolved oxygen levels with oxygenation, and then the other one is without.
And I think we've all seen those kind of nasty streams.
Yeah, exactly. And so that's a bit of a primer. This is the DO sat. This low point here is going to be your D sub C. Again, deficit critical. So you're actually measuring this dimension from the D sat to that point. And then this vertical is whatever DO you're at along the timeline. Okay, so again, that's a bit of a primer on that. So let's take a look at another problem here. And it is a saturated oxygen problem. It says a river that is receiving treated wastewater has the following characteristics just after the discharge point. Assume mixed flow. So like in the first problem, we had to determine mixed flow. I've actually given you the dissolved oxygen that's mixed here. So we have a few data points. Temperature of the water is 15 degrees Celsius. The KD and KR are 0.3 days to -1 and 0.5 days to -1, respectively. And those are characteristic values of the water. And also those are, when we go back to the previous drawing, the KD is the decline rate of this curve. You can almost think of it as the slope, and the KR is the increase rate or the oxygenation rate. KR means reoxygenation rate. KD means the deoxygenation rate. So BODU, that's the ultimate BOD. We talked about BOD before, just a few minutes ago. And then the dissolved oxygen mixed in the stream is 7.5 milligrams per liter. So we want to find that DO, that D sub zero rather, okay, that initial deficit. So I'll just draw a thumbnail sketch of that graph so we can be thinking about that. So we'll have some D sat here. It should be DO sat, sorry. For the dissolved oxygen when it's perfectly aerated, right? And then we're going to have some initial deficit. It's going to have a smile there. And what we need to do is determine what this D sub zero is. Now, there will be a DO at this initial point, okay? So if you look at this, it's a pretty simple equation. It's going to, we're looking for this D0, right? And so we have the dissolved oxygen in this stream. So we have that. We can go look up the DO stat, and then we just determine D sub zero from that. All right. So another way to say it would be mathematically, it would be D sub zero equals DO saturated minus the mixed DO. All right, so let's go look up DO saturated, and I'm going to be using Appendix 22D of the Civil Engineering Reference Manual. And if you look at that, if you're following along on that, then it does, one aspect of it is it's going to be a function of temperature. So DO sat is a function of temperature. It's also a function of the chloride levels. Now, I'm going to assume chloride. We had to make assumptions sometimes on the exam, right? So I'm going to assume that the chloride levels are 0. We have the temperature, so we can then determine that the dissolved oxygen is going to be 10.07 from that appendix. Milligrams per liter being the concentration, or the units. So now we just plug that in, 10.07, and we subtract off the DO of 7.5, both being in milligrams per liter. The value there is going to be 2.57 milligrams per liter. All right. Any questions so far?
I'm checking. We haven't had any questions about DO, BO, anything.
All right, very good.
I am listing the figures and appendix you're listing for people if they are following along. So I know you're not writing that on the screen, but in the chat room, I am trying to follow along with you on where you're headed in this term. So
okay, yeah, and I can write those out if that helps. All right, so let's go ahead and jump to another one. This one is going to be a little more math. So for those of you that like math, we're all engineers, so hopefully, right? So problem 4, distance to DO min. And it says, a river that is receiving treated wastewater has the following characteristics just after the discharge point. Assume mixed flow. So we have basically the same data, all right, if you're noticing a trend here. I'm just adding on a little bit of data, and this is actually the value we just determined. So we have all the same data as before. The only other aspect that was added actually was this velocity of the stream is 0.8 feet per second. So this is a problem where we're going to need to determine two things. Number one, it says distance to the discharge point. Well, we know that we have that graph. Again, here's a thumbnail, that same graph that we've been talking about, and it has the smiley face, and at some time t sub c is when it's at its lowest, right? So we're looking for minimum DO is at that critical time t sub c, all right? Not time of concentration, it's just a t sub c is what it's called, critical time. And so the distance is going to be just distance equals rate times time, right? And that time is going to be, or distance equals velocity times t. And that time is going to be t sub c. So we need to find t sub c first, all right? So in the SERM, that equation is going to be, some people refer to it as the Streeter-Phelps equation, but it's in chapter 28 of this Civil Engineering Reference Manual, and that is equation 28.38. If you're using that book, or other references would include like your Metcalf and Eddy, Drosty's another one. The wastewater books, environmental type books would have that in there as well. So the formula for that, though, is going to be T sub C is equal to 1 over KR minus KD. And that's going to be the log. And it does say base 10 for these. Keep an eye out for that. I noticed one of the 6-minute solve problems actually had this in a natural log and base E. And what they did was they just switched that out for a log base E. So I did notice that, but I kept this one to a base 10. So the KD again, and then here's our BODU, that ultimate BOD. And I'm going to run out of space here, so I'm going to move that. Let's erase that bad boy. Thanks for being patient. Okay, so minus KR times DO plus KD Interesting. I just noticed something. I just noticed that in the equation that I'm using is an algebraic rewrite of this. So I'm going to write it out like this, and I'm going to rewrite it again. So KR, this is the way it looks in the book. KR KD times DO.
What equation are you on there, Andy? And I'll post that.
28.38 in the book. KD times BODU. And then KR over KD. But if, I guess, you move some things around a little bit, simplify it a bit, you end up with a little bit simplified equation. And I actually pulled this out of the example that came right after in the book in chapter 28 of the SERM. So it actually used this slightly varied equation of that. Again, just algebraically done. So I'm going to write it like that. And then again, log base 10. KR over KD. It's a little easier to work with.
That looks a lot easier to work with.
And then KD. I think I got enough parentheses there. Let's see, one more. Okay. So we have all of the information that we need here, and I know the KR and KD are above here, but we just need to plug and chug. We have basically everything we need for the TC. And so we're going to plug those values in. So 1 over the KR was 0.5, and that's days to the -1. Again, I'm not going to write those out, but it is days to the -1, which 1 over days to the -1 is going to give us days. And then the log portion of it is going to be canceling out all the units. So KR over KD is going to cancel out those units, 0.5 over 0.3 there. And then 1 minus the D sub 0, the deficit. Now, we were given that information, which happens to be the same value that we computed on the previous problem, but you can see that this could be a situation where you built up to that D naught and had to determine that in the same problem. And that 1 should be separated from that. So let's clean that up a little bit. In other words, 1 minus the ratio there. And then 0.3 times 10.2. All right, so the DO times KR minus KD is a ratio over KD times BDU. And you're going to subtract that from 1, multiply it by this ratio, and then take the log of that. So I get this first ratio, I get 1 over 0.5 minus 0.3 is 5. And then I get a log 10 of 1.67, which is this ratio. And then this portion here, I got 0.83, which gives us a final time of 0.71 days. Now let's take a look at our units just to confirm that. But if you look at it, we have these both in days. Days, that's going to cancel, right? This is milligrams per liter, DO and BDU. BODU is both milligrams per liter. This is a ratio of days to -1, so those all cancel, giving us a unitless value here for the log. And then as we mentioned before, this 1 over KRKD is basically 1 over days to the -1, which is going to give us days. So our time T sub C is going to be 0.71 days. And remember, all of that was to determine the distance. So distance equals velocities times time. So we need to extend this out and finish this out. So distance, I'm going to write out distance because we got all these D's. Distance equals velocity times time, in this case T sub C. The velocity was given in the problem statement, if you recall, 0.8 feet per second. I am going to write out the units this time because we got to do some units conversions. I generally recommend writing all your units out if you can. It's just, I've already confirmed all of these and I feel confident with it. If I have any question at all, I'm going to write them out. And I would recommend trying to write them out on just about every problem, because I would say that's a killer there is units, as you all know, I'm sure. And so,
yeah, don't get stuck with the units. I guess that's where people think the exam can be tricky if they don't watch those. So make sure you watch those, look at what you're given, and compare that to the answers as well.
Yeah, you can't. And actually, units can be a way to solve a problem sometimes, because you can sort of work your way through that. But yeah, so we have feet per second. We know we need to get that. I'm assuming miles. I know, we didn't give you any multiple choice on this, but if you were to do it in feet, you would realize it's a lot of feet. So that's the reason I converted this to miles, by the way. And so we could have done it in 2 parts, computed the feet, and then what we'd end up with is a really high number. And so just for practical reasons, we converted that to miles. But obviously we need the seconds to days because we have this in days. And then the seconds go away. And then the feet, again, reason for that, which is going to leave us with miles. All right, so doing the math then, we have 9.29 is what I get for the quantity, and miles is our units.
Very nice.
All right.
I haven't seen any questions on this one come in, but if they do, I will pipe up.
All right. Well, we'll take what I'll do is just, again, it's a live, so I thought we could just take 30 seconds to a minute and take a breather. So, but if there's no questions, we'll keep going. But I did want to, I had my levity moment for the day is going to be, I wanted to show everybody my t-shirt. So just for fun. But
hold on, let me get you on here. Hold on.
Oh, you don't have it? Okay.
So let me get you on here. There you go.
All right, hey everybody, I got my t-shirt here and it says, I'm a 3 sig fig kind of guy. So just for fun, this was a triathlon I did a few years ago, and this was the t-shirt we wore. And as I was thinking about civil engineering and the PE exam this morning, I wanted to share that with everybody because I was doing a problem last night. And, you know, a lot of people get on to me about that. Actually, I usually stick to 3 sig figs in my problems, and if I don't, you can get on to me about that. But I usually don't carry it out much more than that. So I don't know how many sig figs you like, but I like 3. So maybe like the 5280 is sig fig. But so just a fun moment.
Was that the team name, Andy?
It was just we came up with a t-shirt for our company. And a couple people up here in the office building that I work in, and it was like 4 of us or 5 of us, and we all ran in that t-shirt. So
nice. I like that.
So
this is awesome. There is a comment here from Kevin. Thanks for the stream. It's helpful to see more depth. I'm guessing most of these are more depth related questions. Yes, I would say so, Kevin.
Yeah, definitely. I mean, I don't know that you're going to see a lot of this on the morning part of the exam, but you know, there's some benefit to this. You can even see like just simple thing like this mixing equation. That's just a weighted average type equation. Some of the tips we've given. So hopefully you can benefit from this, even if you're not taking the water resources depth, but mostly focused on the water resources depth is the focus today.
Yeah, a problem like that, number 1 or 2, does creep up occasionally on a breadth exam. You might not see a huge volume of questions like that, but they can creep up on there.
Mm-hmm.
And like you said, a lot of times if you can work out the units, you can work out some of these kinds of problems. But it is good to know.
Yeah. Okay, so let's keep going. Problem 5, more on oxygen. Okay, so we're going to continue this theme for a couple more problems, actually. And we got the same data as before, again. No new information, looks like. And it says, so same river, same data, and it says find the critical oxygen deficit D sub C. So again, that same graph. Oh, the graph doesn't apply as much anymore on this particular problem, but just so we know what we're looking at, I'll draw it once again. So, and it's that point. Remember that dimension where from D O sat to the bottom of the curve is our D sub C. It's the deficit. It's the difference between the min and the max, basically, the saturated level. So there's an equation for that one. And I believe it's the 28.39 in the book. And so that equation is going to be D sub C.
What was that equation again?
I believe it was 28.39. Let me confirm that.
8.39.
Yes, 28.39. So it's KD times BODU, ultimate BOD, over KR. And then that's going to be times 10 to the negative KD times T sub C, all in the exponent. Okay, so this is just a plug and chug type problem. And again, that was 28.39 was the equation number in the SERM. So KD, KR, we have those. We have BODU in the problem statement, and we have, again, KD again, and then TC. We don't have, but we just computed that, right? So we could go to the previous problem and 0.71 days. So we now have that information. All right. So you can see that this could be a 2-part problem, but I set it up as a 1-part problem here. So we have the T sub C from the previous problem. We're going to plug everything in. So KD 0.3. Again, days to the negative 1. BODU is 10.2 milligrams per liter. KR is 0.5. Negative KD, so 0.3. And TC, again, was 0.71 days. Now, one thing about the PE exam, if you didn't know this, this is not this is actually not going to happen on the PE. You're not going to have to, it's not going to be a problem where one problem is going to rely on the next. Now, they may ask you, they may have a setup like this, and you'll have all the same data, but it would not require a building on of 2 or 3 problems, if that makes sense. So you won't have a second problem wrong because you got the, for example, TC wrong on the previous problem. So that is one good thing about the PE. So I just broke it down into 2 parts just to make, help me with my math checking. 0.61, and then that was 3.7 milligrams per liter. But let's go back and look at our units. Again, I would write it out if you can, just for neatness and time's sake. I did not do that here, but we can do it another way, which is just walk our way through that. So KD, KR both have the same units, which means that unit cancels out, days to the negative 1. BODU is milligrams per liter, which leaves us with that. Over here, the KD is in days to the negative 1, and this is in days, so those cancel out. So we're left with the milligrams per liter as our units. So the quantity is 3.7. The units are milligrams per liter for that.
There's a question on what COD is. What's chemical?
Yeah, chemical oxygen demand. So in the U.S., at least, and I've been out of wastewater for a few years, but at least whenever I was involved in it and whenever I took classes, BOD was the primary value used in the U.S. or the primary parameter used in the U.S. COD is probably a more accurate way of doing it. It stands for chemical oxygen demand, and it's all chemical. I mean, exactly what the word says. So it's all demand of oxygen due to any chemicals, whether it be biochemicals or perhaps other chemical interactions that are occurring. And so it gives you a more accurate view of that. So it's just another way of slicing it. But I've found most of the problems are based on BOD, at least from an organic waste standpoint.
Good.
So minimum DO, again, one more problem on the DO aspect and BOD interchange. So same problem again, just a little bit more information. As you can see, there's that 3.7. So we just added it on. Again, not trying to create a situation where one problem is dependent on the other, but obviously, in the same token, for purpose of studying, I felt that it was good to build on each other in that particular sense. But the way I have it set up, each one of these problems are independent. So that being said, again, our same diagram, hopefully you're not getting too bored of this diagram, but at the same time, hopefully you are learning a lot about DO and this graph, because you can tell it's important. So we have that same value, the DC, the deficit, and then the DO at that critical point, which is what we're looking for here, the minimum DO in the river after the discharge. So once we computed that deficit value, then we know the DSAT, right? We can go back and look that up again, and we can say that in this case, DO is going to be DSAT minus DC, right? So we can write that out and say the DO is going to be DSAT minus the D sub C. Again, we looked up the DSAT earlier, and we had that as 10.07, assuming well, not assuming, but based on the 10 degrees Celsius, or excuse me, 15 degrees Celsius, and then secondly, the assumption of 0 chlorides. We had to make some assumption. So 10.07 milligrams per liter. I will write it out this time. It's only two items to write out. And then the DC that we are given, and of course we could compute it if it wasn't given based on the previous problem. But we do have that as 3.7 milligrams per liter. And doing the math there, 6.37 milligrams per liter. So that's just you think about this problem, very simple math, right? Very simple problem. But we just have a lot of data, right? It could be, is it this one minus this one? Is it this, so it's just understanding the facts and using subtracting the correct two numbers is really all we had to do there, right? That's one aspect of the exam, is really leveraging the ones that you can knock out quickly and moving right along, is one thing that we all want to learn how to do. If you don't know how to do it, then circle back around later potentially.
And I think you bring up a good point about the volume of data. Sometimes they put on a lot of extra data on the problem, and sometimes you don't know if you need it all. So you really have to dive into what they're asking you, and sort that out. Because this might be a water resource type problem, but in other problems, construction, in other areas, transportation, they might throw more data than you need on there. So it's helpful to figure out exactly what they're asking so you can try to go through it quickly.
Yeah, definitely. So one other thing about this problem is 6.37. Again, we said 4 to 6 milligrams per liter was about the minimum for fish and other aquatic life. So it's a good thing that we hit that. It's only going to get better from here because it's going to start reoxygenating with the turbulence in the river and such. So it looks like this river would probably be safe. It could be a qualitative type question, meaning a word problem that just involves words. I call them qualitatives, and then you got your quantitatives, meaning numerical. So this could be a problem where they say, okay, 6.37, is that sufficient for fish life? Or obviously you gotta have four multiple choice question or answers. So I'm sure they would come up with a way of doing that, but just having the knowledge of that could be important on the exam. So thinking back to our original slide with some of the things on there, one was, what is TMDL? So I didn't come up with a multiple choice, but I just asked a question, what is it? So just take a moment to think about that. Does anybody know what TMDL is? We'll give the audience a minute to answer that one.
Start thinking, put on your morning thinking caps. Any answers for the what is TMDL? Get any answers here?
All right, wake up, everybody.
Here we go. They're coming in.
Total maximum data load, yes. So
Robbie says, yeah. Robbie.
Here's a bit of supplemental information. This just comes out for EPA's website. And the TMDL is also related to this concept of oxygenation. What's happened is the Clean Water Act in about the 70s, we were seeing a lot of discharge from different pollutant sources, whether it be a waste treatment plant or chemical plant. It was dumping water into some rivers and other bodies of water, and it was creating unhealthy situations. And so the TMDL is a maximum, as it says here, a maximum amount of pollutant allowed to enter a water body, so it will meet water quality standards for a particular pollutant. So that pollutant might be nitrogen or phosphorus, which you say, well, those don't sound bad. I mean, we have nitrogen in our air, we have phosphorus in our water naturally occurring, but too much of those things can create a real problem that would then cause algal blooms potentially, which would then decrease the oxygen. Obviously, other contaminants would be a problem as well. So it may be just dangerous inherently. Such as so the original slide talked about biological contaminants and chemical contaminants. So like phosphorus and nitrogen would be chemicals that would have a biological aspect to them, meaning they create these algal blooms, right? Whereas, like a PCB, polychlorinated biphenyl, would be a chemical contaminant, of course, that could create really big problems for fish. And then if you eat that fish, it could be unhealthy as well. Did we lose our, did something happen there? Isaac,
No,
with our
I just moved it because you were going on a nice little lecture. I thought people would see your face too.
Okay, yeah. Sorry about that. So that's a little bit of qualitative aspects and some knowledge about, chemical and biological contamination, and then also a little snippet about this aspect of, if you go back to that original slide that I had, that original thing, it talked about, in the specifications, it talks about chemical contaminants, and it says including biomagnification. I think it called it something else. I've always learned it as biomagnification. Bioaccumulation is what they call it. And so bioaccumulation or biomagnification is the concept that, let's imagine of two fish, right? Both eating 1 milligram of PCBs, okay? PCB stands for polychlorinated biphenyls, and it is made from like batteries and electronics being made in chemical, like in plants, right? And so they wash it off and clean it up, and then these PCBs get into the lake or the river, and then two fish come along. They both eat 1 milligram of this stuff, right? And then a bigger fish comes and eats both of those fish. Well, unfortunately, this is soluble in fat, and so it doesn't go away, right? So that fish now obtains 2 milligrams of PCBs, and then you go and catch that fish that same day, right? Or maybe a couple years from now, and now you get 2 milligrams of PCBs. Well, those cause brain problems. So, so it's a real problem to have bioaccumulation, particularly in things like PCBs and things like that. I happen to know a lot about that because I actually did an honors thesis on it in college. So just fun fact. But so that particular one I know a little bit about. But biological contaminants, chemical contaminants, TMDL. Obviously, didn't put the thing there correctly. But we've hit a lot of these today. We've got a couple more minutes. Do we want to keep going and try to hit one more problem?
Yeah,
Isaac?
if you want to knock it out here, it looks like you got, I don't know, 3 more, or what do you?
Yeah, let's see what we can get. This is another qualitative type problem. So we talked a little bit about this already, actually. So I might have given you the answer, but let's see if you can get it. So put your thinking cap on, group, and answer this one if you can. So it says high levels of phosphorus in a body of water can lead to, and then, so this is one type of problem you'll see on the exam. It'll give you 4 choices, and then you'll have to mix them like I have here. So 1 is BOD increase, 2, chlorophyll growth, 3, algal bloom, or 4, oxygen decrease. So A is 1 only, B 1 and 3 only, C 1 through 4, and D none of the above. So which do you think, A, B, C, or D? Let's give the group a chance.
Give them a few minutes. Do. So, Andy, is there a good way to test that fish for PCBs? Because I don't want to be eating some bass and some salmon that's got that in there.
Yeah, I mean, you would have to go over to your local EPA, I suppose, and check that out and see if it's maybe published on the local water quality website. A lot of these, I was actually doing a little YouTubing this morning, and one interesting thing I found out was certain bodies of water that have problems have to publish that onto a form, which I guess is published maybe with one of the government organization. And so I imagine that you can go look that up. But as far as individual fish, I mean, it would be difficult to test that out. So unfortunately, but more if you are really concerned about that, you may want to check it out with your local government or EPA. So any guesses on that yet? Looks like
I've seen a guess of C.
Okay. All right. Well, let's see. It's actually all 4. So phosphorus in a body of water is going to help create the algal bloom, which is another name for chlorophyll. So kind of not trying to trick you, but somewhat of a trick question there. Chlorophyll and algal, they go hand in hand. They are basically the same thing, which is going to increase the BOD, the demand, and it's going to decrease the oxygen. So it's actually all 4 of them. So C. Is that what they said, C?
Yep.
All right, so they're correct. Good work. So here's just another photo. Here's a photograph and a little information there for the group. This just came off the EPA site. Nutrient pollution issue shows a picture of algal growth, what that would look like. Not something you probably want to go swimming in necessarily. And it comes from, where does phosphorus come from? Well, agriculture, putting nitrogen, phosphorus, or nitrogen and phosphorus both cause the algal blooms and algal growth. But these are some of the sources of that. So agriculture, but also it can come from the home. So pet waste, soaps, detergents. It got a big kick. I remember maybe 90s or so. I remember seeing a lot more about the detergents with the phosphorus and nitrogen in it. I haven't seen it as much lately. Maybe I haven't really paid attention to it, but it's something that you can, if you're concerned about that, you can watch even your amount of nitrogen and phosphorus you put into the water supply. So
we've got a big problem here in Utah. There's a lake called Utah Lake, and it's always on the news with some random algae bloom that's going on over there. So yeah, these things kind of hit home sometimes.
Yeah. All right, let's see if we can knock at least one of these out. That last one's a qualitative, so we might better knock this out. Let's see, we just got about 4 more minutes.
Yep.
So this is a disinfection problem and a bit of a stretch, but we're disinfection, which is a biological, we disinfect for biological contamination, basically, is the tie-in there. So, and on the exam, it's not like they're looking at this list that we have at the beginning and necessarily following it to a T. It's more like a guide. So be careful of that. If you're like, oh, that wasn't on the list, it's everything's fair game, so be ready for anything, right, Isaac?
Yep. You'll be taken off guard maybe with a few that you're like, what?
So what we see here is a chlorination basin is used to disinfect wastewater prior to discharging into a local stream. The characteristics are temperature, 15 degrees, pH 8, CT value is 122, a flow rate of 3 mgd. What is the amount of chlorine in pounds per day needed if the local standards require 2 milligrams per liter effluent concentration? So a chlorination basin would, it would have some baffles in it. It would go along the baffles in order to create a well, not always, but a lot of times you'll see what we call plug flow, which is what I'm showing here. So anyway, it would go around those baffles and it would come out of there. So we have a flow rate given of 3 mgd. We have a CT of 122, and we have other data there. So first thing we want to do is determine, so it's asking for how much chlorine in pounds per day do we need. And that will be the concentration, C naught. So on the beginning side, we'll have a C naught, and then we'll have a CF. Well, they gave us the CF, and this is probably the, I guess, trick to this one, if you want to call it that. But they gave us the CF of 2 milligrams per liter. We need to know what the C naught is, and so, or the initial, the pounds required per day is going to be equal to, so it's going to be equal to Q, quantity of chlorine, QC, is actually going to be, interestingly, Q times C naught. That's just a coincidence more than anything. So our Q is an mgd, 3 times 10 to the 6, or gallons per day, and then that's going to be multiplied times the concentration initial, which is, now I pulled this out of a different book. There's not a whole lot that you'll find in the Civil Engineering Reference Manual on that. So if you have this book, you can use it, or you can just write it down here. But the C naught is equal to C final times E to the KTD. So TD is the detention time, which we need that as well in order to solve for this C naught. So the CF we have to, the K is a function of the water. I did not give that to you, and so that we would need to give that to you actually. It's going to be 0.25. It's a function of the wastewater. So the K would be 0.25, and then the TD you would need to determine. So I'm going to leave a space for that because we need to compute that. So that is going to be a function of this CT value. CT is a value that helps you get to, it's found from testing basically of that wastewater, again, much like the K value. So what we would do is that would be given for us. And so the time is going to be the CT over C. So you can see the C's kind of cancel, and you're left with the time. So we know the CT value of 122. We know the concentration, which is the final concentration is what we're going to use there, is 2 milligrams per liter, which is going to leave us with 61, and that's in minutes. So they would need to give that to us as well. So 61 minutes. We'd plug that in here, and then I get a C naught of 2.58 milligrams per liter. Then we plug that in here. We get our units, obviously 3.3 times 10 to the 6 gallons per day, much like the one we did before. I'm going to say 2.58 milligrams per liter. We're going to multiply by a few factors. So 3.79 gallons, or 3.79 liter per gallon. And then 454 times 10 to the third milligrams per pound. So, and then we would, cancel out the appropriate ones: liters, milligrams, day, or actually day doesn't get canceled. So that leaves us with pounds and day. So that'll be pounds per day. And then I get a value of 64.6. is the amount of chlorine used.
Perfect.
So that one I worked a little bit faster, just for time's sake. And then the final one just says which pathogen is used for evaluation of disinfection and inactivation. So like if you want a 90%, 99.9%, we heard a lot about that this year with the virus. But if you want a 99.9%, it's based on disinfection inactivation is usually based on which one? A, Salmonella, B, E. coli, C, cholera, or D, Giardia lamblia.
Yeah, there's a question real quick from Kelly about which book you were referencing. Problem 9 was from, you said, or?
Yeah, I used a book called Drosty. It's Ronald Drosty was the reference I used for that, and it's a wastewater book. And that equation was 10.4 F.
How do you spell his name? Ronald.
Droste.
Okay, you got it. I put it in the comments.
All right, and then the answer to that one is Giardia on that last one.
Cool. Well, let's go ahead and wrap this up. I know we've hit over an hour, so like I said earlier, thanks for being on here. Thanks for being part of the workshop. We'll continue to do some more in the future. In fact, Andy's coming back on the 22nd and the 28th, and we'll be doing structural as well as construction. So we'll hit some more problems in the future. If you want access to these recordings, we'll have them on our social channels for a little while, but eventually they will find themselves in our course. So if you need that, go check it out, civilengineeringacademy.com. Kevin says, what was the answer to number 10 again? Sorry, I missed that.
That one was the Giardia. I think it was D.
D. Giardia. You do not want to get Giardia.
No, you do not.
That'll ruin your day. Anyway, guys, we'll go and wrap it up. Anything else, Andy?
No, I appreciate it, Isaac, and thanks everybody. Hope the best for you on your PE exam. Check out Isaac's information, and then if you got any other questions, give us a shout. Hopefully this was helpful for you today. Give us some feedback so we can improve it and make it better. So yeah, hopefully you're on track to passing that PE exam. Just a few months to go, so keep studying, keep working hard. Let us know if we can do anything for you.
Okay, we'll go ahead and wrap this up. Thanks everybody for joining. See ya.